Okay, hello everybody. We'll get started right on time since I know one of you has your honors thesis after this. So welcome to the 2023 Spring Semester Showcase for Project Cities and the town of Gilbert. I'm Julia Gilbert, the Program Manager for Project Cities. We have a great chemical engineering, process engineering capstone class here, as well as one of our reps from the town of Gilbert. So today, next slide. So we've been working with the town of Gilbert. This is our first semester actually with them. So we're excited for your project to be one of our inaugural projects with them. And the town has really shown commitment to wanting to bring sustainability more into its practices and efforts. So we look forward to continued partnership with them now and into the future. And then Paul, I'm gonna pick on you in a minute to just be like, say a few words just as a heads up. So this project this semester was focused on waste diversion opportunities. For a little bit of background, I worked with Paul Montez and to set up this project. And initially, we had sort of framed it as two different projects. So the feasibility of building a MRF and the feasibility of Gilbert building their own landfill. But then whenever we met up with your professor, Dr. David Taylor, we actually figured out that it would make more sense to have this kind of combined project, leveraging your very like big picture thinking, process engineering sort of focus. So for this project, the different goals were first to explore innovative opportunities for waste diversion, whether it's recycling, circular economy, landfill, those sorts of things, determining the feasibility of these different things. And then the most important one, I think, especially for chemical engineering, is figuring out how to create value from that waste stream feed for the town of Gilbert, which is something that towns don't often get to sit and think about for a long time. So we're excited to hear what you all have today. Paul, do you want to say anything before I have an intro video from David?
I just want to thank you all for this opportunity to partner with you all. Sorry.
You're good.
To partner with you all. Oftentimes in my day-to-day work and being in the industry for so long, I often get tunnel vision and I can't break way out of that tunnel and think of the long-term opportunities that are out there or opportunities that are unknown to me yet, but working with all of you with the resources that you have and the vision that you have, that's a great opportunity for us to learn more and see what else is out there for us. So thank you all for doing such great work.
Great, thank you. I won't pick on you yet. And then we have a quick introductory video from Dr. David Taylor, who's their professor. He is teaching their class right now at this moment. So thank you all for using your class time for this. So we'll play this video and then we'll start with the first student presentation.
Hello, everyone. My name is Dr. David Taylor, and I'm an associate teaching professor at Arizona State University with a background in chemical engineering. One of the classes I teach at ASU is the Capstone Chemical Engineering Design course, and it is part of this course that most of the work being presented today was completed for. The course itself gives students the opportunity to work with and work on a semester-long open-ended design project where the students are expected to make and justify all pertinent design decisions. Students have the option to choose between several different design challenges, but the goal of the course is to give students the opportunity to apply the skills that they've developed during their time at ASU to relevant engineering issues. The students who are presenting today represent some of our most outstanding and highest achieving students. And of the 114 students in my class, these are the 10 that formally agreed to participate in this design challenge and accept the additional responsibilities that are associated with the project. This demonstrates a willingness to go above and beyond the requirements of the course, which can be especially tricky considering that this is the last semester before most of these students will graduate. Hallie, Hanley, John, Lucas, Jimmy, Rashab, Andrew, Kenneth, and the Joels, thank you all for putting in the extra effort and hard work in most of your final semesters. I'd also like to thank Paul Montez and everyone in the City of Gilbert who had a hand in helping to develop this opportunity for my students. And finally, a huge thank you to Julia Gilbert for helping to coordinate everything. I can't wait to work with you on future projects in future semesters. Thank you so much, everybody. Enjoy the presentation and cheers.
Thanks, David, even though he's not here. So we have our first group. Are you the waste wizards or you're the waste wizards?
We are Sparky.
You're Sparky Solutions. Okay. I love it.
Oh, you guys switch it.
Yeah, one of them has an honors thesis right now.
Gotcha.
Yeah. So then, yeah, as I think we mentioned earlier to folks, so the way that the camera is set up is it's going to be over here, and then I will make sure that you.
Morning, Ann.
Good morning.
Sorry.
Oh, it
So
doesn't
pretty
show
much-
up on the screen though.
No, it
And
just
then
has
I got
to be right
focus
here
on
too, so stay like
Teams
with
meeting
the.
and then I'm like running
And
around.
then I would say.
I'm gonna stand.
This is exciting.
I hope we were probably just
This
coffee.
is
Alright.
This is really cool.
So, hello, we are the team Sparky Solutions, and we decided to try and go with MSW pyrolysis. And we'll explain what that is as we go. I myself am Kenneth Scott.
I'm Joel. I'm Joel.
I'm Rashawn. And I'm Andrew. So, we're going to go ahead and walk you through. We have an introduction on pyrolysis. We then have our process flow diagram, or PFD, along with a stream table for our overall balances. We have a sectionalized review of our process to go over 5 split up divisions. And then we have our manufacturing cost summary, an investment summary, and an equipment summary, as well as our conclusions and recommendations. So to start off, restating that problem statement was to identify a value add opportunity for the municipal solid waste that is already collected. And we wanted to describe the process needed to convert the waste into a desired product that can be value add. And what we chose for our personal project basis objectives was prioritizing diverting waste from landfills. Secondly, producing energy dense renewable energy resources and reducing greenhouse emissions. So a little pyrolysis introduction. Pyrolysis is specifically the decomposition of organic materials through anaerobic heating. All that means is you get things that are made out of carbon compounds and you get them very hot without oxygen present. So that prevents the normal combustion or fire that would occur. And what that ends up producing, as you can see in the equation there, if you look on the right side of it, it produces bio-oil, biochar, ash, as well as you see carbon monoxide, carbon dioxide, hydrogen, and a little bit of methane, which is CH4. And that's called syngas. Those gases together are synthetic natural gas. In our final pyrolysis plant design, we ended up with an average profit of about $750,000, whereas Gilbert's current, where they sell the OCC in paper, is about $700,000 per year. And our suggested implementation would require first combining with other municipalities with their MSW to reach greater profitability.
So what does our overall process look like? From a very high level perspective, on the left in that green box, we take in the mixed municipal solid waste. That's all of your glass, aluminum, plastics, cardboard, paper. And then on the far right, we make 2 useful products. Those are the blue boxes. We make syngas, which is the synthetic natural gas, and then the bio-oil, which is kind of like a natural gasoline substitute. And so to do that, let's walk through the process and see how kind of each step of that occurs. So first of all, we take in that mixed, I can't really see it, but you take in that mixed municipal solid waste and we put it through a series of separators like eddy currents, knife crushers, and we basically remove everything besides the OCC, the old corrugated cardboard, and the paper. And so the rest of the municipal solid waste can be disposed of either in the landfill or sold according to current methods. We then dry and crush the paper and cardboard to reduce the moisture content and reduce the particle size. We take that mixture of dry cardboard and paper particles and put it into what's called a pyrolysis reactor. So we heat it and use the high temperature to thermally decompose the organic components to turn it into some of the useful products. So from the bottom of that reactor into that red box, we output solid biochar and ash, which we can't use entirely in our process as it's currently designed, so we probably will send it to a landfill for now. And then out the top of that reactor will come the syngas and the vaporized bio-oil in both a gaseous phase. So we take those substances and we cool them down to recondense the bio-oil into a liquid while the syngas remains gaseous, and put it through a flash drum, which will separate the components by their phases. And so this part is where our process kind of splits into 2 major sections. So we can see out the bottom, the crude bio-oil comes in a liquid phase, and out the top comes the syngas. So in the bottom of the process, we take that crude liquid bio-oil and put it through what's called fractional distillation. which is where essentially we reheat the process to upgrade the oil into a more pure and usable form that can be sold. And then we take the condensed water from that process and refilter it through our design as coolers for our heat exchangers. At the top of the flash drum, we take the crude syngas and put it through a series of separations to basically purify and remove pollutants from the gas. First, there's a CO2 adsorption column where we use a physical zeolite, which basically captures carbon dioxide, a little bit of methane and nitrogen, and removes them to just prevent the release of greenhouse gases. After that, it goes through a dihydrogen sulfide column, which removes dihydrogen sulfide, which is a toxic pollutant that you don't want to release into the atmosphere according to the EPA. And finally, it goes through one final syngas purification step, where we remove some of the gaseous tar, which is still remaining in the gas, and that basically improves the purity and heating value of our syngas product. And that's the output of our final syngas.
So here you can look at our overall stream tables. This is the main inlet and the overall outlets of our process. So you can see on the left, we take in the MSW at 18 or roughly 19 tons per year. About 10 tons of that is the OCC and paper, which is why we chose to simplify this process down to just those two. And then on our product outlet, you can see the major products that we have are syngas, bio-oil, and then below in the waste outlet, we have biochar and water. Water would be released as vapor through the drying processes. And the bio-oil, to give you an idea of the scale of this, that's about 21,000 barrels per year of oil. It sounds like a lot, but in reality, most very small scale petroleum facilities produce about 10,000 barrels of oil a day. So it's pretty small. So it would be highly ideal to get some more MSW inlet so that this could be increased. Also, the bio-oil wouldn't just be one type of oil. It's not like it produces just gasoline. It produces on a spectrum of oils of different densities. So things like jet fuel, gasoline, kerosene, all of those. So not all of those would be used in tandem. So here's our section-wise review. We sort of broke it down into 5 sections, one for each of us. We start with our MSW separation. We then have the pyrolysis reactor. Then it splits off to the fractional distillation and the absorption, and then the final syngas purification.
So for the municipal solid waste separation process, 3 alternative designs were considered to optimize the base case design, which is this figure on the upper right corner illustrates a visual of how a base case design for a municipal solid waste separation process would look like. And these alternatives were ranked on 3 criteria, which are the energy consumption, the maintenance cost, and the initial equipment cost. Being the energy consumption given the most importance, due to that it would account for the most expense as time progresses. And the 3 alternatives were the addition of an optical separator, the use of a different drying mechanism, and the utilization of shredders as opposed to crushers in the base case design. And it was concluded that the addition of an optical separator was the best alternative as it reduced the personal operation cost significantly while not raising the initial equipment cost or the energy consumption too much.
So now going to the pyrolysis reactor, we based it on 3 optimizations, which are the product yield, cost to purchase the equipment, and cost of maintenance. So we looked at 4 different reactors, which were the rotating cone reactor, the fluidized bed reactor, the cyclone/vortex reactor, and the ablative plate reactor. And we decided that for our base case design, we chose the rotating cone reactor, and there are reasons to this. First off, we have a higher purchasing cost of $150,000, and I know that may sound very expensive, right? But if you look at other reactors, such as the fluidized bed, the cyclone and vortex reactor, and the ablative plate reactor, they cost anywhere between $90,000 to $110,000 on average. Additionally, despite the higher purchasing cost of the rotating cone reactor, it has a lower maintenance cost. So to maintain it, the rotating cone reactor costs $70,000, whereas for the other reactors, it ranges from anywhere between $72K to $85K. And according to various literature studies, it has been repeatedly found that the rotating cone reactor can produce a higher yield of bio-oil in comparison to the other reactors. Now, here are some applications of the rotating cone reactor. So this reactor it's pretty new, but it's being used in other parts of the world. For example, currently a company in the Netherlands known as BTGBTL is converting sustainable biomass into biooil using a rotating cone reactor. And many pyrolysis plants in Malaysia are also implementing this reactor. So they're taking fruit branches from palm trees and at a 50 ton per day capacity to produce this biooil.
So going into our fractional distillation section, like I said, it separates liquids by density into multiple outlets. So that's how you end up with the different fuels. It's used often in the petroleum industry for that exact reason. The biocrude inlet we get is estimated purely on the outlet of intermediate pyrolysis of MSW. Values vary massively throughout literature. So depending on your feed and depending on your process, you can end up with anywhere from 20% to 60% bio-oil outlet. And there's no way to analytically determine that due to all the differences that can be in your feed. So the only way to really do that is test it. Also, all of this is relatively new in the sense of industry. There's a couple of pilot plants that are out there that currently use pyrolysis. However, our plant would be the first that would do MSW specifically. Most of them currently, like Rashab said, with the rotating cone reactor, use garden waste or other forest waste, so mainly wood. Other considerations that we did for the fractional distillation was considering burning the biocrude oil, but that was seen as very wasteful as biocrude is our primary profit, and all the CO2 would end up being released, which sort of negates the whole purpose of doing this. And in gasification, that would turn bio-oil into syngas. So we could have one pure outlet rather than two separate ones. However, with that one, it once again has about 40% of the carbon would be turned into carbon dioxide and would end up being released. And syngas is also less valuable than biocrude per kilogram. So we decided not to do that.
So once again, the pollutant absorption section, its main purpose was to physically capture and remove the greenhouse gases such as carbon dioxide, a little bit of methane, and the toxic pollutants like dihydrogen sulfide according to EPA regulations. So we wanted to mainly remove these gases that we didn't want to release into the atmosphere and to make a safer and more sustainable process. And the way that works is we use packing material in towers, which is essentially will physically or chemically attach to the specific gases we choose and prevent them from leaving the column. So only the gases we do want, the carbon monoxide and the hydrogen, will be able to leave our process successfully. The rest of it we can dispose of according to hazardous waste guidelines. A few other design considerations were considered, such as selective methane separation, but that's kind of a newer process that's too experimental. It uses a lot of membranes and stuff, which is very complicated for a large process. And we also thought about increasing the size of your dihydrogen sulfide column, but ultimately the price was too high to meet the need.
So our final step in purifying the syngas is the removal of tar. So tar here is classified as these hydrocarbon chains. So if you see here, here's our tar. And what this does is if we were to sell our syngas with this tar, it would reduce the efficiency of our syngas when it would burn, and thus people wouldn't be willing to pay as much for it. So we want to remove this tar to add value to our product. So taking this into account, the efficiency of the removal was the most important factor in analyzing different options. So our base case design used vegetable oil, which has lipophilicity properties, which is able to dissolve the nonpolar hydrocarbons, which is also known as tar. So other factors taken into account were the energy and the utility required to use this purification process, as well as the cost of the material. We see three other options were analyzed. The soybean oil operates very similarly to vegetable oil. However, it isn't quite as efficient. Our vegetable oil was able to achieve 95% efficiency, according to literature, where soybean oil was around 90% efficiency. Zeolite and porous material are other purification possibilities. However, those were also around 90% removal efficiency and were also more expensive.
So up next, we have the manufacturing cost summary, where the annual revenue comes from selling the products produced, which are bio oil, at an assumed price of $2 per kilogram, purified syngas at an assumed price of $1.5 per kilogram, and the high pressure steam raised by the heat exchangers. The annual expenses considered were the column packing, the tar absorbent, equipment electricity, personal salaries, waste treatment, and equipment repair. The annual profit comes from the difference between the annual revenue and the annual expenses, and would be approximately $6.6 million. Some of the manufacturing cost summary shown on the previous slide, there were certain additional factors that were not considered that would certainly alter the results. Some of these additional factors would be the depreciation value of the plant, inflation, taxation rate, and an annual interest rate from the initial loan. The figure illustrated above shows a cash flow diagram, which was generated by an Excel economic tool named CapCost that does take into consideration these additional factors. And this cash flow diagram depicts a yearly cash flow of approximately $750,000 per year at an assumed plant life of 20 years and a 2-year construction time.
So in regard to our investment summary, before we dive into it, it's important to define two concepts known as the total grassroots cost and the total module cost. So a total grassroots, total module cost is basically the expenses that are associated with modules, materials, labor, installation, and manufacturing. Whereas a total grassroots cost is like constructing the plant from the ground up, like including like building the facility at the plant site. So now that you have some context of what these two concepts are, we can see that the total grassroots cost has approximately a value of $2.5 million, whereas the total module cost is about $1.7 million. So it makes sense why the total grassroots cost is more expensive than the total module cost, because especially when you're building an industrial plant from the ground up, there's going to be more costs associated with that. Now, if you look at the cost to purchase land at Gilbert, it's at $2 million. And we also looked at the regional commodity pricing as well. So as you are potentially aware, the profits of selling the old corrugated cardboard and the old newsprint is relatively small. So we believe that this pyrolysis plant can bring significant value, specifically to this fraction of the municipal solid waste.
So going through some of the equipment that are needed in this process, through the MSW separation, which Joel talked about, we need various metal conveyor belts, knife crushers, and then the various separations. So this is all just to separate, so we just get down to our dry OCC and paper. And we also have our pyrolysis reactor, which is a rotating cone reactor. Next, we move on to our fractional distillation. And this had 20 trays, and we see that the diameter is only about 6 inches. And for industrial standards, this is tiny. And this is because we have a very small total flow rate through our process, as Kenneth was saying earlier. Whereas if we were to expand this, this is one of the columns that would definitely be increased more to industrial size as we have more of an industrial flow rate. We also see for the pollutant absorption, we have the CO2 absorption column as well as the dihydrogen sulfide column. We see our dihydrogen sulfide column is as well very small, around 1 meter cubed. We then move on to the syngas purification, which uses a 2-stage vegetable oil scrubber. Essentially, the syngas will flow through 2 of these tanks that have vegetable oil in it, and the tar will be just entrapped in the vegetable oil. These are both around 170 liters. And other equipment that was needed in this process was 2 cooling heat exchangers. As Kenneth was talking about, when we first come out of the reactor, we need to cool down. So in order to cool this down, we use some of that recycled water to transfer the heat from the gas to that water, which is able to raise steam. And from this raised steam, we're able to sell that at a profit. In addition, we need 2 heaters, which are used for the separation processes as well as the reactor. We needed 2 pumps as well as a flash drum.
So I know that's a lot of nitty-gritty detail, so let's zoom back out and look at some of the accomplishments of a high-level perspective of our plant. So we divert almost 8,000 tons per year of the municipal solid waste, which represents about a 41.4% diversion of the overall inlet MSW. Additionally, we produce almost 5,000 tons per year of reusable biofuels, and from the product inlet, that's about a 45.5% yield from the municipal solid waste that enters our plant to the biofuels that exit. And finally, the syngas we produce has composition values that are very close to what literature expects and desires. You can see that each of the component gases is within a few percent. The methane's a little bit high, but that'll just increase the heating value and provide a little bit extra energy. So overall, very successful plant.
In conclusion, we believe that an intermediate pyrolysis plant can be a viable option for the town of Gilbert, as it would reduce the landfill waste, generate clean energy, promote sustainable development, as well as reducing its greenhouse gas emissions. We also believe that the plant should not be constructed unless more consideration is given on expanding its MSW intake volume, as this would increase its profitability.
And we have some recommendations as well. So one, we want the plan to essentially consider expanding the feed plastics other than polyvinyl chloride, known as PVC, as well as consider garden waste and food waste. Additionally, we will want an analysis of an MSW sample. Well, this is what we recommend. That way you can have a definite amount of syngas and bio from the MSW feedstock. And when you conduct this analysis, you're going to get 3 contents, which is the moisture content, the organic content, and the ash content. Primarily the parameter that is of most value is the organic content, especially when you're dealing with hydrocarbons and garden waste and food waste. And additionally, we recommend collecting and incinerating the biochar and ash, because this is going to generate additional electricity and potentially assist in powering the plant.
Thank you.
You want me to ask a question now or wait until the time?
No, we will do questions now. We have about 12 minutes for this.
Oh, may I? Thank you.
Yeah, go ahead. Do you want to introduce yourself too? Yes.
I'm just a random person just walking. Good morning, everyone. My name is Yafan. I grew up in Tempe. I went to Clinton, I went to ASU, received my civil engineering degree. So I worked 10 years in the consultant side, and then the last 20 plus years I've been on the dirty side, which is the public side of things. So right now, my current position is I'm the assistant public works director in overseeing solid waste, streets, and fleet and safety. But I also touch base with our water wastewater team. Ann and I go way back. We partner with a bunch of projects with the city of Patch Junction that I was the city engineer director of anyway. So going back, this is the first endeavor. Super excited, super geeked up. It's helping us actually, because in context, real quick, the background is that Paul and I are in negotiation with City of Mesa for MRF. It's a facilities. We're trying to control costs, and that facility is around $90 million. Right now, it's strategic place in East Mesa where there's a railroad line. And so what you guys are doing and kind of suggesting, there's a lot of synergy. It can be doable, right? And so that's something that it gives us more options. The way that we look at trash, and again, I'm ignorant to the trash industry, Paul's an expert. We have to look at it because of the recent 5 years of the market condition, it's kind of flipped on its head. We were at one time making money off of recycled goods and materials. That industry has changed quite a bit. Now it's a negative, not a positive for us, right? And so now we have to look at it from a field point of view, right? It's a resource. So to have, and then with your studies and with your paper, it's going to help us kind of like look at it differently, which is a great thing. So that being said, that's where we're coming from.
Do you have questions?
I do. Just some notes, the scalability on material. I know that you looked at it as, hey, look, the plant's going to go in X amount of material. But I like the fact that you guys look at it from a material expanded, but what about volume, right? From a scalability wise,
Yes.
right? Because a developer or an owner, they're gonna look at the initial capital cost, okay? What's the bare bone minimum of that? And then as they increase their volume and other material, that's gonna increase costs. I mean, it's gonna increase profit. So there's gonna be a threshold where what's the initial investment, right? Versus moving forward with, they can make more money, right? So, when you guys, the other process, when you start to change this from a waste material to a fuel, you guys are gonna inject certain, like whether it's water or electricity, you're gonna to convert this, right? Again, my knowledge, I apologize, my knowledge of chemistry, it's been a while, so.
Your engineering classes
Yeah,
are coming
yeah,
back.
so-
Yeah.
So again, when you add more, like, to change this particular commodity into a usable commodity, right? You need to input some sort of other energy or water, whatever, right? And to me, the question is sustainability, is because a couple factors that poses threats is that regulations, right? We don't know what the EPA mandates are. Right now, we assume a certain usage of ability of the usage of this information, right? Or of this industry, but then we don't know what it's going to be as far as the cost of the resources that you guys need to convert this into a profitable product. The unknown about the regulations. And then the last thing is that when you talk about site at $2 million, you guys, I'm glad you guys, are ASU, but you can see the land prices in around Gilbert. A house is $1 million, right? So there's a factor that you might want to consider is that the site, if we get it out towards the boonies, which people are going to like that better because no one wants to live next to an incinerator, right? Okay, so now you have a logistic issue, right? You got to factor in as far as that cost as well too, because the farther you're out, the more that you have to spend money up front to transport all that goods and services.
That's one of the biggest costs of most of these pyrolysis plants.
Yes.
So there's currently a pilot plant operating in Canada. They're planning on scaling them up to 4 full-size plants by 2030. And they're generally the biggest issue with all of these plants is being close enough to the material that's being generated, right? Because it is very expensive to transfer all that mass.
And with the numbers that you guys showed up, are those minimum amount of volume of materials that you need to keep that going? Because the reason why is that, let's say it becomes more of the economy flips on its head again, right? Now it becomes a more of a profitable with just the way it is. So now Paul's gonna make a decision. It's like, okay, I'm making profit, requires less. So do we turn out the plant, right? So that's the balance that we always go to, right?
Yeah.
So just thoughts. I mean, the graphics were really good.
We have another CFD if you're interested. So right here, this is actually a cash flow diagram. This one takes into account the time value of money. If you're familiar with that concept. So taking into account the time value of money, essentially, if you put this money into the bank getting, or the market getting a 10% return, our average yearly cash flow would drop down to about $350,000 per year. That's on top of like the 10% increase. But of course, these are, since we have so little statistics and data to go off of, all of these values are going to be plus or minus anywhere to 50%. Because this is a very, very rough draft. Like I said, I mean, the bio oil outlet could end up being 60%. I believe we assumed about 40%.
Give me like 25 maybe.
Yeah, and then you guys could end up going through testing out these materials and see, it's actually only a like 10% bio oil outlet. So there's fortunately, that's pretty easy to test. In fact, we have a lab here on campus, Professor Dang, which Andrew and I are joining his lab. They test that themselves. So it's something that you're able to get if this is something you're more interested in. However, it is very experimental. All of this is very pilot plant technology.
And that's the concern that we have, because a lot of times when we go to our elected council, when they're elected officials, to add for capital, right? They're gonna look at data points. They're gonna say, okay, so who in the valley or who in the region is using that, right? And it's hard to convince them when you have a new technology of less than a year, because we don't know what the implications are from maintenance, from sustainability, right? And so that's the worry. You know, sometimes it's tough when you have this great idea, innovation, and then it just takes 5 or 6 years to build on data points, right? Is the do's and don'ts.
Certainly, we wanted to give a more far off. So if Gilbert ends up deciding to do something in the short term, but then comes back to this problem in maybe a decade, maybe past 2030, when there are more plants that are fully operational like this could be sort of a reminder of what exists as a potential. These technologies aren't brand new. Like the pyrolysis reactor we use, I believe, was designed in the 1980s. The issue is no one has been able to, or had the motivation to scale these up into larger plants, because there hasn't really been a reason to, when oil is comparatively so cheap.
The application for this is that because we're one of multiple cities in the valley, so
Certainly.
collectively, that's where it's our job as to build that relationship where it's easier if we have a regional facility, right? It makes a lot more economic sense, right?
Yeah, and they said to put in all the MSW from all the different places like that.
But then the kids, and like the officials, we have all egos, right? It's like, well, we could do it better than everybody else, right? So that's the stupid thing about the politics, right?
We wanted to go separate because their team presents on a incineration plant, which is a tested technology that you guys can easily find a lot more data points for. But instead of providing two very similar presentations on essentially the same topic of incineration, we wanted to go on that more experimental side, give you guys an idea of maybe the can gets kicked down the road, because that happens a lot in governmental issues and decisions. And if it ends up getting kicked down the road enough, then this may be something that's more viable.
And I'm glad you mentioned that because.
This is your last question for them.
Sorry, I'm rambling here. It's the coffee kicking in. It's got a lot of synergy because in our wastewater team, we're having discussion with a bunch of outside vendors of converting that into some sort of gas instead of energy source. I was talking to our water manager earlier this morning. Desalination plants, right? At one time in the back of the 80s, that was the way to handle shortage of water. It was very cost prohibitive, but now with a shortage of water, it starts to make it look more reasonable now, right? It's the same thing with this type
Certainly.
of concept, right? At a later date, it will be.
Along with the acts that are getting passed in Congress, we've had a lot of them that are a lot more pro renewable resources. So if there ends up being things that provide more subsidies to plants like this, that could end up making it a lot more feasible. I know recently there was the bill that passed that was designed at making hydrogen, green hydrogen, a lot more effective in plant operation.
And when you talk about like convincing like city officials, especially, one thing, as I mentioned, if you go into the applications of the rotating cone reactor slide, I talked about that one company in the Netherlands called BTG BTL, right? And relatively, like for the most part, we use intermediate pyrolysis, whereas they use fast pyrolysis, right? But when they built their plant, right, what they've seen, I don't remember like the exact statistics off the top of my head, but what they have seen is that other companies started shifting around that area, and they were purchasing the oil from their plants. So in terms of like an economic standpoint, that like those cities, wherever they expanded to, there was like a significant economic benefit and economic growth.
Sorry, no more questions or comments. I'm sorry.
Yeah, no, you're all good. Paul, do you have any comments?
Yeah,
or
I just want to say
questions?
this is pretty amazing. I don't actually understand the process that you guys were talking about. It's above my
He did
head.
read your report. He was like, it was a little over my head, and I was like, me too, but this is great. Looks
But it is great. But I just want to share with you that even if it's not in the near term or short term, immediate future, something like this, if it was to be put on the back burner, I'll just share with you that like the MRF and transfer station that Deputy Director Mr. Yalfam had talked about, has been on the back burner since the early 2000s. And it now is coming to discussion as a possibility in the near future. So this type of thinking is very valuable. And I'll share with you with the energy shortage, fuel shortage. Imagine if your police department or fire department didn't have fuel to make those service calls. That was a situation recently where that was a possibility, where fuel was being threatened and it wasn't in immediate supply. But this could help to shore up those essential services where the fuel is immediately there.
Yeah, typically with bio oil, you tend to mix it with the current petrol. And I believe the typical amount you can mix up to is like 20% of the bio oil.
So it's very relevant what you're talking about. So this is exciting. Thank you.
Yeah, I just have a couple of comments, and I'm Ann. I'm the director of Project Cities.
She's a big deal.
She's not. But this is
Big, big.
really amazing. I loved your presentation. I have a couple comments though. You mentioned green waste, which for the valley, we have an issue with palm fronds like crazy. So I'm curious, number one, if that is an option in taking care of that issue, that portion of waste stream, because that is one area cities have a tremendous problem trying to figure out what to do with. And it all goes to landfill. The other one is air quality. We have ozone issues here. And so if you're talking about incineration, that could pose a bit of an issue.
They do incineration. Our
Okay.
process would only release water.
Okay.
It would release just steam, similar to
That's
like
awesome.
a nuclear plant. The feed can be anything that's organic. You could throw table in there, and as long as it's made of wood, it would still.
That's
So
awesome.
plastics are made out of carbons that have been formed into long chains as polymers. Those can work. The only reason why PVC doesn't work is because it's half chlorine, which is very noxious. So it's not in the sense that it just physically doesn't work. It's just, it's going to cause more pollutants in your gas that you're going to have to take out. So it's just not really economical. And then garden waste can include anything from lawn clippings to palm fronds to anything like that. Anything organic could go in this, including food waste like old
Yeah.
burgers.
Which like the East Valley doesn't necessarily have a big collective green waste.
Yeah.
For right now, so it's gonna be cool.
And then for your vegetable oil,
Yes.
I was curious, is that something where that could be recycled vegetable oil? So you have different
Almost certainly.
restaurants in the valley that could actually feed that process, so to speak, that resource. So you're helping solve one issue in providing that for your facility. So that's another thought that I have. And then greenhouse gas emissions are going to be becoming more and more important, I think, for cities and towns to calculate, reduce, and so forth. So did you look at all into the carbon neutrality of this particular process?
So generally, I believe pyrolysis is considered fairly carbon neutral in the sense of the carbon dioxide basically trapped in the plant, and then you basically release it again when you burn it. So it's kind of neutral in that sense if you aren't releasing more than was already in the atmosphere, because to grow the plants, you need to take in the carbon. We also tried to remove, I think it's about 60% of the carbon dioxide that we release. So in that sense, we try to approach carbon negative process, but may not be perfect. But we're trying.
Sure. Thank you.
Okay, well, great, round of applause for this.
Hi everyone, we're the Waste Wizards and our project was Waste Diversion for the town of Gilbert. I'm Jamie, this is Hallie, Hanley, and John. Lucas is sick today, so we will be presenting his section. So here's an overview. We will be going over the background, purpose, and main objectives. Next, we will discuss the optimizations and final design of our project. Lastly, we will conclude on the economics and summarize the key findings and future recommendations.
So in the town of Gilbert, there are around 270,000 residents, as you guys know, and that number is continually increasing. And so we wanted to come up with a system to deal with the 3,000 tons of municipal solid waste that are produced weekly. And so currently, of those 3,000 tons, only around 12% of that waste is being recycled. And so with this in mind, after collaborating, came up with 3 goals that we wanted our design to address. So first, we wanted to minimize the amount of waste that was sent directly to the landfill, because currently 88% of those 3,000 tons go directly to landfills. And then we also wanted to reduce the environmental impact of what happens with the MSW. Landfills are heavily responsible for methane emissions in the United States, which is not good for air quality and pollution. And so that was another goal. And then lastly, we wanted to maximize profits for the town of Gilbert. We wanted to design a system that would be profitable and be able to last throughout the years. And so we developed a waste to energy facility that has 6 main sections. And in this facility, the waste is taken in, it's burned, and the heat that's generated is eventually converted into electricity. And so the first section is the feed stage, which has the mechanical claw and hoppers. And then it's section 200, which is the actual incinerator. Then the heat exchange system, and then the next is flue gas treatment, which includes a scrubber, a baghouse, and a stack. And then it's section 500, which is the power generation section, which includes a steam turbine and generator. And that is our most profitable section, because that is where the electricity is generated. And then we have the separation stage, which is section 600, includes a rotating drum and eddy current system. This is our last effort to get the metal out, and so we can also sell that for a profit. So as Hallie said, section 100 is the feed stage of the plant. And in this stage, the garbage trucks will bring the waste and drop it on the tipping floor / storage pit area. And then a mechanical claw will move the waste into hoppers to be fed directly into the combustion chamber. So when designing this section, we had 4 main design criteria that we really wanted to look at. And the one that came out to be the most important was efficiency. And this was because we really wanted to make sure that we were able to effectively move the material from point A to point B without a lot of issues and without causing backup for the rest of the plant. Safety risk, capacity, and technological readiness were all really important too, because they all really impact our ability to be able to move the material. For the final design for section 100, for the mechanical claw, we initially looked at 3 different designs. We had a pneumatic gripper, a hydraulic gripper, and then an automated hydraulic gripper. What we found is that the hydraulic gripper was the best design to go with, and this is because it had a better gripping strength than the pneumatic gripper, and it was better able to handle the quantity that we needed it to. For a similar reason, the automated hydraulic gripper was slightly below the normal hydraulic gripper, and this is because the automated portion of the 3rd design was not as well known and researched, so we just decided to go with the hydraulic gripper that is just like manually operated, just to be sure that it was going to work. For the hoppers, we also looked at 3 different designs. We looked at the steepness of the walls. So for the first one, we had a steep back wall. The second one, we had a steep front wall. And then the 3rd design, we had both a steep front and back wall. What we found was that when both of the walls are steep, it allows for a more continual flow of the material. And so that way we'll have a more steady stream into the combustion chamber. And this was really important just to help maintain the steady state value of our plant. In the figure, you can see the mechanical claw grabbing the waste and moving it into a hopper.
The next section is the combustion chamber. As you can see in figure 4, we have 3,000 tons of mixed MSW entering the incinerator. In addition, 20,000 tons of air, 40% in excess oxygen enters the incinerator. As a result, we have around 23,000 tons of flue gas and fly ash and 720 tons of bottom ash. Below you can see the criteria. The most important design criteria was waste incineration rate. It was important to deal with and process as much waste as possible. Next was robustness, safety risk, and low cost. In figure 5, you can see the waste incineration in action. On the far left side, you can see waste being dispensed. As it moves through the incinerator, it's being burned, and it is turning into the flue gas, fly ash, and bottom ash. As a side note, the thermal efficiency of typical incinerators are about 74%. We decided to choose the MSW incinerator due to its ability to process as much MSW. It's a continuous reactor, so it's able to process a lot. Next, we have the rotary Kin incinerator. It's also a continuous combustion reactor. However, it is typically more expensive and not as used often as the MSW incinerator. Lastly, we have the modular incinerator. It operates in batches. However, it lacks in waste incineration rate, but it has longer residence time. So the ash volume is going to be smaller, but we chose the MSW incinerator.
So the next section is the heat exchange system, and as you can kind of see in figure 7, the system is actually built into the incinerator. The tubes line the walls, and so as the water travels through the tubes, it's converted to steam. And for the system, we wanted a really high efficiency. As you can kind of see in figure 6, the water that enters is converted into steam. And we wanted high efficiency because the steam goes on in later sections to actually produce the electricity. And so when we were designing this system, we looked at 4 design criteria. The most important one was the lifespan of the material, and we rated this the highest because we wanted not to have to continually replace this system, mainly due to its high cost, and also that would create additional downtime of the plant. And then we also wanted the system to have a high thermal conductivity value. The thermal conductivity of the material directly relates to the amount of heat transfer that can occur. So the higher the thermal conductivity, we'll get a higher heat transfer rate. That will produce more steam, and then eventually that will produce more electricity to be sold. And then we also wanted a high Reynolds number value. This relates to the mixing in the tubes because a higher Reynolds number relates to higher mixing, and that will result in more steam production too. And then lastly, we wanted a high flow rate of cooling water. So the more water we can move through the system and convert more steam, the more electricity we can generate and eventually sell. And so with this in mind, we came up with 3 designs. We varied the type of material between ceramic and steel, and the type of flow between turbulent and laminar. And so the steel and turbulent design was better than the other 2. When you look at the ceramic and turbulent design, the steel and turbulent design was better because it had a higher heat transfer rate and a longer lifespan when compared to the ceramic material. The ceramic did not hold up very well. And then when compared to the steel and laminar design, the steel and turbulent design had a much higher mixing in the tubes. And as you can kind of see in figure 8, the turbulent flow allows for more mixing and more heat transfer to take place. So for these reasons, we went with the steel and turbulent design for the heat exchange system.
So after the flue gas passes through the heat exchanger, there's going to be a lot of pollutants in that airstream. We need to remove those before we can go ahead and release the treated air to the environment. We do this in 3 stages. Our first stage is a wet scrubber, which uses a scrubbing agent to remove pollutants. Second stage is going to be the baghouse filter, which is going to remove any physical contaminants such as fly ash and dust. And then finally, we have the stack itself, which is going to lift the treated air up and release it at an altitude where wind speeds are higher to aid in dispersion. At the top, you can see we have our mass balance for the flue gas treatment. The flue gas comes in, is scrubbed with the sodium hydroxide scrubbing solution, and wastewater comes out as well as the scrubbed flue gas. And then you also go into the baghouse, which has a filter cake as a byproduct. This filter cake is going to be combined with the bottom ash from the incinerator and sent to the landfill. Those are the only 2 things that are sent to the landfill. And then finally, we have the treated air coming out of the top of the stack. And that is usually monitored to make sure it is below EPA regulations. At the bottom, you have our criteria that we use to go ahead and optimize our piece of equipment. For the scrubber in the baghouse, we have amount of chemical species removed as the highest at 45%. Regulatory requirements met, safety and ease in operations, and equipment costs are also some other criteria we had. For the stack, the lifespan was the most important criteria at 47%. And then we also have maintenance requirements, equipment costs, and total height of the stack. So for our scrubber optimization, we looked at 3 different designs: the Venturi scrubber, the seawater FGD, and the packed bed wet scrubber. You can't see it, it's hidden behind the little screen right there, but there's a star by the packed bed wet scrubber indicating that that's the one we chose. The reason is because a packed bed wet scrubber is going to have the added benefit of increased contact time between the scrubbing liquid and the flue gas itself. This makes the packed bed wet scrubber much more efficient when compared to the other two. So for instance, if you had a packed bed wet scrubber and a Venturi scrubber that were the same size, let's say the Venturi scrubber only removes 90% of pollutants, the packed bed wet scrubber would be most likely over 99.9% efficient. So that's why we chose that one. And the seawater FGD scored the lowest because it only specializes in removing sulfur dioxide. So it's just not going to work for our purposes. For the baghouse design, we have the pulse jet, the reverse air, and the shaker baghouse. These three names really refer to how the baghouse is cleaned to remove the filter cake. Pulse jet uses compressed air. Reverse air is literally just ran backwards to remove the filter cake. And then the shaker baghouse just literally jiggles it back and forth to remove it. We chose the shaker baghouse as the most efficient because you don't have to shut down the system in order to clean it, and also it's the easiest to maintain. For the stack of the system, so there's two different criteria that really go into this. There's the construction, which is either going to be steel or concrete. We chose steel because steel has a longer lifespan of rated over 30 plus years, where concrete is generally only related to 25 years. And then also you notice the two on the right say wet stack with reheating or concrete stack with reheating. That reheating basically means that you have to reheat the flue gas in order to get it to go out the top of the chimney, which increased your cost. We chose the one on the left, wet stack with 45-degree high velocity pattern. This is new emerging technology, and it allows the stack to operate at higher wind speeds, which is going to eliminate the need for your reheating system. So we chose that one because it's going to have much cheaper cost.
Next, we have power generation. This section dealt with power generation through using a steam turbine and an electric generator. So as you can see in figure 12, the mass diagram, we have steam entering the turbine, which produces mechanical energy, and the electric generator converts the mechanical energy into usable electrical energy, which the city of Gilbert can sell. Below are the design criteria. The efficiency was the most important. For the steam turbine, we were talking about the isentropic efficiency, and for the electric generator, it's the motor efficiency. Next, we have technological readiness. It had to be existing and low risk. Next, we have life expectancy and maintenance demand. So the final design for section 500, we had mid-size condensing turbine, extraction condensing turbine, and geared turbine. We chose the geared turbine due to its high efficiency. It's able to maintain constant and high spinning, which results in the high efficiency, and it required minimal maintenance. And for the generator, we decided to choose the double fed induction because it was bidirectional and had consistent power output.
So for the final section, section 600, we looked at the bottom ash and middle separation unit. So this section basically takes all of the bottom ash generated in the combustion chamber and filters it through two pieces of equipment. The first piece of equipment is a rotating drum magnet, and this is useful in separating ferrous metals. And then the remaining mixed bottom ash will be sent through the eddy current system, which will be able to remove non-ferrous metals. So when designing this, it was really important to us that we were able to remove the most amount of metals, but both to be putting less waste into the landfill and to help optimize our profits. So for that reason, environmental impact came out to be our top design criteria, because that really demonstrates how much of the metals we remove. And then for a similar reason, capacity and efficiency were right behind it, and low cost came out to be the least important because our focus was removing the metals. So for the final design for section 600, we looked at 3 different designs for the rotating drum magnet. For each of these designs, the main difference between them is the magnetic strength. What we found is that it would be better for us to use a stronger magnet so that we are able to remove a greater amount of the ferrous metals. So the extreme deep reach intensity magnet was the strongest magnet, and it's able to remove ferrous metals that are both really large or really fine from thick flow streams. The other two magnet strengths aren't able to remove fine pieces from thick flow streams, so we just went with the highest magnet to be able to remove the most. A similar method was used for the eddy current system, as we looked at different magnet strengths and lengths. For the eddy current system, the same decision was decided on, and this is that the longest and the strongest magnets would be the best. And this is because the longest strong rare earth magnets enable us to have a strong magnetic field both on the surface of the belt and above the surface of the belt. The other two designs there that aren't starred, they only have a strong magnetic field on the surface of the belt or above the surface of the belt, but not both. So we ultimately went with both of the strongest magnets for both of these pieces of equipment, as it enabled us to remove most of the metals.
Looking at the economics of the waste energy plant, you can see that we do have a yearly income, but we also have a large initial investment cost. I'm going to break down these numbers a little bit for you. So for your yearly revenue, you have $4.3 million. Most of this comes from sale of electricity from the generator at $2.7 million. The remainder of that is due to recovered metal sales to like scrapyards. And then we also have an annual cost of $3.8 million. Again here, the majority of this comes from personnel and also the utilities on the heat exchanger, which really takes up a lot of the cost at $3 million. And the remainder, $800,000, is really going to be just upkeep of the facility and like maintenance. Taking these two numbers together, we have a yearly income of $500,000. But like I said, there is a large investment cost of just over $90 million. This is mainly due to the equipment cost. You can see almost $60 million, and installation of that equipment at almost $30 million. So those two numbers right there is really the majority of that cost. And there is something kind of non-monetary about the system that we'd also like to say, is we're reducing the amount of waste that's sent to the landfill by quite a bit. The 3,000 tons that we're burning goes down to just roughly over 700 tons that's actually sent to the landfill. So that's reduced by 2/3 the amount. In conclusion, we believe this is a good idea for the town of Gilbert because it meets our objectives. Like I said, a lot of the waste is reduced that's being sent to the landfill. Also, any of the pollutants that are recovered in the flue gas treatment are going to be halted from actually making it into the environment. This includes all the methane that would be released if like organic waste was sent to the landfill, which is basically going to be methane, which then converts into CO2 over its lifespan. And also the town of Gilbert would be able to make a profit using this design. For recommendations, so we have some improvements that could possibly be implemented in the term of recycle streams. So the flue gas treatment can have a recycle stream added for its wastewater that comes out of the scrubber, which can then be reused and will reduce the need to deal with hazardous waste as often. We can also add a recycle stream to the heat exchanger as well, which will reduce water costs or water need of the plant. We also recommend that the town of Gilbert would go ahead and pair with other cities in the nearby to go ahead and handle the large investment costs. And also the plant is not really operating at capacity, so it could handle more waste. So in that would also improve the amount of electricity that's generated as well. And then also, as it is right now, the plastics are just being burned. So you could actually do a combination of the two where they would be separated, and plastics could possibly be recycled, and then you could also use some more organic waste to be converted into biofuel as they suggested. And then also, once the plant is up and running, it really would be a matter of constant improvements because all this stuff that we're doing is based off of other facilities that are in operation, and it might not be an exact one-to-one comparison of what we're actually burning. So we went worst case scenario for all of our sections. So in reality, it will probably end up being a better situation than this, but we just wanted to plan for the worst. Thank you. Any questions?
Got like 15 minutes.
I will allow our colleagues to go first. Paul, Ann?
Not questions, but just, again, the process little over here, but, I'll share that about 2005 or 2006, we did a waste study, with the city of Mesa. An organization had, approached us for a waste to energy facility that they wanted to put next to the SRP plant in Gilbert. At that time, there wasn't enough volume for it. So they didn't think it was a feasible project to continue with. That was back in 2005, 2006. I think there are cities and towns have grown since then.
Just a little.
Yeah, just a little bit, but also, and I just learned this not earlier this week, is that another one of our divisions in the town of Public Works, I believe they pay over $1 million a year for some of the electricity for the streetlights and traffic signals, things in the right of way. So we're paying a cost for all of that, but if we have like a waste energy plant, I can reduce those costs so we can capture that energy, and then also reduce our landfill fees, which were about $2 to 3 million a year. So there's already savings already at that front end. So I think that's
If I may,
great work.
one of the costs that you guys are not aware of, and you should be, is that our tipping fees, the fees that the landfills charge us, have gone up by quite a bit, a double, quadruple.
What are
Just in the
they now?
past year or two, yeah.
3601, I believe.
And so we can't control that, right? And so part of that mitigation of that initial capital cost of 90 million is that, hey, look, you're reducing your annual cost. And again, that's a unknown that we can't budget for, right? And so that's a good point to convince, right? To trigger the project. I like the fact that your presentation was into the process for us selecting the different processes and how you have that design criteria. What's different about Gilbert compared to other organizations is that we have a lot of smart people from the private side. And to eliminate the politics, it's information decision making, right? That we have the data and allow all of our division with Public Works, the next couple of years going to be having more data analyst people to help with our operation team to gather that data, so the way we look at trends, we look at smart decision making, and then that eliminates the politics, right? Here's the pros, here's the cons, here's why. If you don't do it, it's gonna cost you 10 times more, right? It's simple, right? Eventually emotions will wane, logic will succeed, right? And so it's a pleasant thing, right? But so based on that, I like the fact that you guys, a lot of your processes, you guys did decision-making criteria. It's always good, right? It's always gonna say, hey, look, we selected this part of it, this process or equipment based on criteria, which is always helpful, right? So that's great that you guys did that. The gripper, and then again, me not being a mechanical engineer, more of a civil, is that, and Paul knows this, is that the more hydraulic stuff, it tends to break down. It's just the more overusage. We have trash trucks that are picking up trash cans, 1,000, 1,200 cans a day, 5 days, 6 days a week. And eventually those trash trucks, these $500,000 trash trucks, break down within 4 or 5 years, right? And so those are the things as you guys look at that, right? Maybe it looks good from a volume, from a point of view, but also really pay attention to the maintenance costs, the wear and tear of each of this process, right? And so you guys did a really good job of that. The mere fact that when you guys presented, the purpose was clearly stated. So it's always good to connect with the audience, say, hey, look, this is what we're all about. This is our mission. This is what we're going to cover, right? I like the fact that that you were different from the other team was that you had a more specific with the internal process versus the other team where they had a global, more of a broader, wider approach, right? Different process, different approach, and it works. And then the other thing is that you hit it, and I want to note when you said about it might not look on paper to be so much profits, but here's the win is that we're only making $500,000, right, for a $92 million, $90 million capital cost. But the indirect benefit is that we're reducing waste, right? In Gilbert, and Julia and Ann knows this, in Gilbert, we're a very conservative organization. Saving the environment should be a byproduct. For them to connect, it has to save them money, right? And so to me, that's how you approach a lot of getting to know that organization is how do we approach it? Is it economics or is it more that they're more progressive? It's more about the environment. So you have to change your message, right? As you present this on who your target audience is.
Right.
If it's a bunch of engineers, okay, you hit them hard with technical stuff. If it's a bunch of like people that are more soft skilled, they're like, okay, let's look at the nice flowers, right? I mean, I joke around, right? But that's the key, right? And so the last thing I want to say is that taken from this is that both teams, you have to change as far as that there's both teams presented processes different ways. The way that we could do it, it could be a hybrid solution, right? Like you mentioned that there are materials that it's of value now. Let's pull it from the waste stream. If there's no value, we could always burn it and create energy.
Right.
So that's a takeaway. That's a huge takeaway for us because Paul knows this is that at one time glass, cardboards were of huge demands. Now cardboard not so much because of the overabundance of supply.
Right.
So now it's considered to be rubbish, which is a good terminology, right? But that, yeah, we're going through a renaming brand. So I got shut down because we were going from environmental services to trash and recycle, and solid waste and recycle. And I wanted to use the word rubbish because it's very
Right, yeah.
Yeah.
the whole team just shoot it down. Our director, Paul's like, no, that's just trash, yeah. There's a scar from it. But going back from that is that talking about the scalability and flexibility, as we go through this, that's what we need to do is right now, maybe 5 of those commodities are of value. Eventually, some of them won't be. And so we're able, a plant or a process needs to change depending on the condition moving forward.
Right.
So.
Yeah, and I feel like that would build, especially regionally, resiliency moving forward, because yeah, if the market turns around and glass is like, you get a lot of money for it in the future, awesome, but if it doesn't, then what do you have as your backups to make sure like Gilbert, Mesa, or whatever other communities you want to collaborate with on these types of things all have inputs where you're making money from it continuously. Because right now, even if you do that $90 million facility with Mesa, like you're still paying tipping fees for it. Like it's not like, so even this, if you make some money from it, like I'm not in your department, you have other considerations, but at that point, you're still losing money on all of the current waste streams right now.
And mitigating our annual cost is one thing, right? Where if our tipping fees are increasing 15, 20%, if we can reduce it where it's flat for the next 5 years, that's worth a consideration, right? So.
Yeah, and the incineration plant technology has just gotten so much better over the years. Like I'm sure the 2005 pitch was different than this type of thing. But again, I'm not in that field directly. But
CO2 capture is a lot better.
yes, yeah, because it used to just be like, oh well, we'll figure it out.
Other comments, questions?
And do you have an air pump of it? Oh, okay.
But I wanted to share with you that in the heart of Gilbert on Galveston and Southern, there's an 8-acre landfill that is just barren land. There's nothing we can do with the land anymore. They had this conversation yesterday. What could we possibly put there? But saving the land for usable space rather than a landfill, that alone has a huge impact on the environment. So any of these two solutions here for our waste has a lot more value than just dollars. So.
And you own it already? It's just the city owned?
That's a county landfill.
Okay.
I really liked your video graphics. For a non-technical person, that really helps me understand what you're talking about. So I would suggest if you do this in front of a set of, staff or leadership, you include those kind of visuals to make it a little easier for us lay people to understand. I was very impressed with it. Waste to energy has been a rather controversial area, I think, ever since I came to the Valley, which was
2 years ago.
yeah, early 90s. So a very long time when recycling and trash was, kind of up and coming. So I think its time has come. So the reception might be a little different than previously, especially when it, comes to carbon neutrality and air quality. The science behind it has gotten so much better. So I think the combination of approaches is really interesting and could be looked into more from a financial aspect.
And it makes a lot of sense, right? Because there are things that are known technology that we're going to go with, and then eventually you can morph it into more sustainable, right? Technology. Going with what Anna and Paul said is that, believe it or not, hopefully if we don't implement it in the next 5-10 years, it could be 15 years from now, but at least that thought process needs to be documented. If you look at the Salt River, your peers back in the 70s, it was all landfill. Your peers in architecture, my understanding is that the architectural college here had a bunch of graduate smart people like you guys had an idea of the whole design of reusing one that was barren, that was pollutant. We had a lot of trash in the Salt River right now, right? The Rio Salado. And then think about it, you guys think it's like, oh, it's a nice recreational asset now, right? Versus that was something that was negative, right? And so to me, that was 40 years ago, right? And so for you guys, this is a good way of like looking at it differently, where hopefully we'll learn from our mistakes and then implement sooner rather than later. But it's a chance, another idea, right? That's really cool.
This is really good timing too, even though, especially with the federal infrastructure money is coming down through the Biden administration. A lot of it is transportation related, but there are opportunities for other types of infrastructure development. So depending on how the cities and maybe the region twist and turn the project, you might be able to easily apply for some assessment, even some planning type grants to get this kind of facility started.
And Jack, what Anne's saying is that there's a lot of federal funding out there. I wish we as a town or organization, we had more people on staff to look at that, right? So Paul, I'm talking about Paul, is like, he is, so his struggle is like trying to balance the sheet every year, right? His struggle is trying to make sure that he's got enough operators, his leaders, his supervisors, superintendent has enough operators to pick up the trash every day to mitigate the increase in the construction costs. When does he have time to look at the bigger picture, right? And so that's the struggle that we have for all of our line of services. Is when do you press that pause of just trying not to keep the organization afloat, right? Versus taking a step, 5 steps ahead in the future, right? And so that's always a struggle with our leadership, is that I have to do a better job of giving more time to brainstorm and to make a difference, right?
So you work with us.
I know, hey, slowly, okay, Julia, okay, but that's something that we're working on, right? That is that we're trying to give them more ideas, and so that way we can bring it back to our teams to try to implement it.
Well, we have, I think I had this end at 10:30, we have about 5 minutes. Do you have any questions for the other group, or if the groups have anything they want to add? Now's a great time for that. Great job overall. So, any other comments?
Can we get this in PDF? Because
Okay.
I would love to share with our other managers in the different lines of services.
Yes, you'll get their slide decks and their written reports from their class and the video.
And then down the road, I'm going to share it with our economic development team, because we have a lot of private company that comes to us, ideas that are not as vetted out as what you guys presented. And so that's something that I'll be mindful of copyrighted stuff and everything else. But to me, sharing is caring is hopefully somebody, right, a company will take on these concepts and then maybe make it profitable for them and help us in as well too.
Anything else you want to add about any? Okay, I think we're good. We'll round of applause again.